Problem 1.2 refers to example 1.2, which we dealt with earlier. It involves a continuous distribution of photos taken at random on a rock as it falls down a cliff. Now, this is dealing with a continuous distribution rather than a discrete one, so there are a few differences. But let's just start right away with part A. So part A wants us to find the standard deviation of the distribution from the example. We know the formula for the standard deviation. We know that it is sigma equals the square root of the average of j squared subtracted by the average of j itself and then squared. So obviously the formulas for finding the average are a little bit different when we do continuous as opposed to discrete distributions. So let's start off by defining the discrete variant. So for discrete distributions, move that right down here, and we know that the average of j for a discrete distribution is equal to a summation in j of j itself times the probability of j. And if we wanted to move on to a continuous distribution, we would evidently have to turn our summation into an integral. So for continuous distributions, what we get instead is that the average of j is equivalent to the integral from negative infinity to infinity of j times, instead of p of j, this time we say rho of j, where rho of j is our probability distribution of j, times dj. So evidently, the process of finding the standard deviation is kind of the same thing. The only difference is that we have to solve for these integrals. Now, from the example, which if you don't know what it is, you should probably watch the example video I did for example 1.2. But we already know that the probability distribution of x, where x is the distance the rock has fallen, is equal to 1 over 2 times the square root of h times x, where h is the height of the cliff, x is the distance it has fallen, and we know that x is constrained on the interval from 0 to h. After all, our rock cannot fall a length greater than the length of the cliff, and it cannot fall upwards either. So evidently what we want to find is then are two variables. The first one is the average of x squared, and the second one is the average of x itself squared. Well, we can start right away with the simpler one, which is the one in green, the average of x itself squared. So we know that we can set up our equation as follows. So we know that we can set up the average of x is going to be equal to the integral, this time not from negative infinity to infinity, but from 0 to h, because that's the only interval in which our analysis is valid. We stick an x in here, and then we multiply by the probability distribution of 1 over 2 square root of hx dx. And if we were just to go on from here and plug this into an integral calculator, this would give us the equivalent of h over 3. And since we are looking for the squared value of this, what we know is that the average of x itself squared is simply equal to h squared divided by 9. Moving on, finding the value of x squared, average, is kind of analogous. The integral is just a little bit more complicated. We are dealing with an integral, same thing, 0 to h, but this time instead of x, we put in x squared, and then we multiply it by 2 over square root of hx, and the dx. And once again, for the purpose of this, just to kind of make this entire process a little bit less painful, I will simply plug this into an integral calculator. You would obviously be encouraged to actually do the integral yourself, but for all intents and purposes of the fact that we're studying quantum mechanics and not the math class, I will not do integrals like this because they're simply a little bit too trivial to actually go over in detail. But this will equal h hat, or h squared, over 5. And if we plug this into our standard deviation, we know that the standard deviation, let's do this in a different color, we know that the standard deviation is equal to the square root of x squared subtracted by x average squared. We plug in the stuff that we found above, so this equals the square root of h squared over 5 minus h over 3. And this gives us approximately 0.2981 h. And that is our answer. Okay, so now let's work on part B. What is the probability that a photograph selected at random would show a distance x more than one standard deviation away from the average? So, to kind of give a visual on this, I will start by drawing out the probability distribution that we defined in example 1.2, and we said that the resulting distribution looks something like this, where there's a very high probability of finding the position of our rock to be higher up on the cliff, and a gradually exponentially lowering probability of finding it farther out. And this is the probability of finding us at some value x. So let's say that our average is somewhere here. Let's say that this is the average value of our x. Well, what this question is then asking us is, what is the probability of finding x to be more than one standard deviation away from the average? So let's define 2 more points. Let's say that this point represents x minus a standard deviation, and let's say that this point over here represents x plus a standard deviation. So what our question is actually asking is, what is the probability of finding our position x in the region right before it and the region right after it? So evidently we can do this as an integral, and we can say, well, our probability is going to be equal to the integral starting at x equals 0. Let's write the probability equals here. Probability equals to x from 0 to x minus our standard deviation of our probability distribution, dx, and then added with our integral from x plus 1 standard deviation all the way to infinity, or in this case at h, because we're only defined up to h, of rho of x dx. And this is 2 integrals. We can actually simplify this a little bit, make our lives a little bit easier, if instead we define this as 1 minus the integral from x minus the standard deviation to x plus 1 standard deviation of rho of x dx. And effectively what I'm doing here is I'm defining the probability of finding x inside my inside the region where I don't want to find it, and since probabilities have to always add up to 1, I simply take 1, which is the maximum probability, and I subtract from it the probability of finding the particle inside this standard deviation region. And what remains has to be the green probability, which is what we actually want. And what we can do here is we already know that the standard deviation is 0.2981 h, and we also know that the average of x from here with this integral is actually h over 3. So we can actually numerically calculate what x plus standard deviation is and what average x minus standard deviation is. And as it turns out, x plus a standard deviation is equal to 0.6315 h. And if you don't believe me, you can kind of do this calculation yourself to verify. And the average of x minus a standard deviation is equal to 0.0352 h. So our probability ends up being equal to 1 minus the integral of 0.0352 h to 0.6315 h. And then rho of x dx, well, we know what rho of x is. It is 1 over 2 times square root of hx. So 1 over 2 square root of hx dx. And if we were to plug this, let's just plug this into a calculator and solve it directly. What this gives us is 0.393. And you might be a little bit concerned about the fact that we had an h variable inside of our integral, but it doesn't seem to appear here. But if you just do the integral out fully, what you'll find is that there's a term square root of h over square root of h, and as it turns out, the height of the cliff actually doesn't matter in regards to this calculation.